quadratic formula. That's great, right? When you're learning math, do you want to learn from somebody who's memorized a quadratic formula or can actually derive it for you? I mean, do you want someone who understands it at that level where they can show you where it comes from, or they just, hey, here's a formula, let's use it? So I try and avoid formulas as much as I can if I can force you to think a little bit more, like force you to actually geometrically see it. So I'm just trying to tell you, that's the reason why. I think it's more constructive for you. Yes?
You're trying to give us the fishing pole rather than the fish, as it were.
There you go, yeah. I guess so you could look at it that way. All right, and look at this next thing that we have, because this next one, you're going to see that you really have to understand this idea that the integral is just a tool to add things up. The formula that's inside the integral can be anything you want, right? We've been doing volumes, but now let's just take a look at this next example of, these are called cross-section problems. And they're really kind of interesting, I think, because I'm going to ask you to do a problem with it. And you know what? Let's start with the problem. Let's start with the actual problem. And then you'll see maybe why this might be valuable. I'm going to turn off the lights real quick. I hope that didn't seem like a dismissive answer to you. I'm trying to get you to understand. I mean, yes, there's probably a way we could get a formula somehow. But, yeah. All right, so here's a problem that you're going to be asked to do. I have two pipes. These pipes both have a radius of 1. Okay, so the radius from the center to the outer edge there is 1. Both of these pipes are 4 units long. Okay, we'll just say feet to make this easy, all right? The radius of these pipes are 1 foot radius, and the length from the edge to the other edge on both pipes is 4 feet. And my question is, what is the volume of this? So when you look at that, there's a problem, right? Like, if I asked you to find the volume of one of those, could you? Sure, right? Like, find the volume of the blue one. Great, you could do that, right? You don't even need calculus for that. Find the volume of the red one, yeah, you could do that. They'd have the same volumes, wouldn't they? But the problem here is that they intersect each other. So there's a shared volume, right? You can't count it twice. You can't just find the volume of the red and the blue added up, right? You've doubled something there, haven't you? So you need to figure out what's the volume of what they have in common. So what I'm asking you is, if you look at this, what is the volume of that piece in there, right? That's what they share. If you could figure out what the volume of that is, that could help you, couldn't it? That could help you figure this out. So how do you figure out the volume of that shape? Do you all see that this is not a volume of a solid of revolution? Like, that doesn't look like something that's just been revolved around an axis. It's got a really weird shape to it. So what we could maybe do is use some of the symmetry that we have in here, and maybe we could figure out just what the volume of, like, just that one piece is. See that one piece there? How many of those pieces would we have in this picture? We should have 8 of them, right? There should be 4 of those pieces on top, and there should be 4 on the bottom, right? So, but how would you find the volume of that, right? That seems like a weird kind of shape. It's not like an everyday shape, right? It's not a box. It's not a... That also doesn't look like a solid that we've revolved. So that's our motivation, all right? Our motivation is, could we figure out the volume of something like that? And now what I'm going to do is show you. Come on. There we go. So let me write the problem first, and then we'll kind of try and wrap our heads around it. The base of a solid, this is no more revolving, okay? We're not doing that. This is a new concept. The base of a solid is the region bounded by y equals x squared minus 1 and y equals 1 minus x squared. So I want you to imagine a solid, all right? A solid object. And here it is. I'm going to just set it on the ground, okay? There it is. And what I'm telling you about this solid is that the base of the solid, the part that's touching the ground, is the region bounded by those two curves. So let me draw those curves real quick. Those are both parabolas, right? Okay, this is a parabola, opens up. It's been moved down 1. So it looks like this. By the way, I'm not trying to do that problem right now. That was motivation for this idea, all right? But this idea is not for that problem. All right, so now I'm going to take the other one. That's a parabola, opens down, has been moved up 1, and it goes like this. Right? There's the graph. So do you see the region bounded by the two, right? That's what the base of this solid looks like. So the bottom of the solid looks like that region. All right, great. Now, cross sections perpendicular to the x-axis form squares. Find the volume of this solid. Okay, so let's try and understand what they're saying to us here. So, right, I've got this object that's on the ground, and that's what the footprint, right? That's what the footprint of this thing looks like on the ground. And it's saying that what we're given is that when we take a cross section perpendicular to the x-axis, so if I come in here and I were to get some magic samurai sword here and do a cut, right? I'm going to cut through this solid. I don't know what this solid looks like, okay, above. I just know that's what it looks like on the ground. If I cut this with the sword, right, and I make sure my sword is perpendicular to the x-axis, so I take a cross section through the x-axis, I cut through, right, cut it. Imagine taking one side and just throwing it away and looking at it from the side. The cross section, the shape I see is a square. Okay, it's a square. The question is, if that's the case for everywhere I cut it, I see a square. So imagine I just cut at this little edge right here. I take that piece off and I look at it from the side. I'm going to see a big square, small square? Little small square, right? But if I cut it here, take that edge and throw it away and look at it from the side, am I going to see a big square or small square? Bigger, right? Bigger square. And so the question is, if that's the description of this object, what's the volume of it? So I have a better kind of animation for you that will help you see this a little bit better. That's the way the problem is presented in the textbook, all right? Where is it? Cross sections. There we go. So there's our curves, right? Sorry, the colors don't match. Oh wait, they do. They do? Yeah, I just got lucky. All right, so there it is. That's the ground, right? That's the base of the solid right there. And when I do cross sections, it forms rectangles. Let me see if I can make this a little bit bigger for us. Okay, sorry, not rectangles, squares. I wanted squares, right? So when we look up from the side, you see it's square? And that would be everywhere I cut it. So no matter where I cut it, right? See the squares? Whoa, shit, I don't know why I did that. Okay, see how the squares will get bigger and smaller the whole time as I move through depending on where the cut is. All right, so what would all of those together look like? Well, probably something like, imagine all those, well, that doesn't help. Imagine all those squares. Maybe I'll bring the grid in there. That's all the squares together. I get that weird shape. Do you see my cuts in there? Squares the whole time, comes down the edge, real small squares. I would like to know, what is the volume of that very odd shape? Seem reasonable? Do you understand the geometry right now behind the word problem? Does this word problem make sense now? Base of a solid, right? cross-sections perpendicular to the x-axis form squares. What if I said they form something else, like equilateral triangles? It wouldn't look like that anymore, would it? Right? So what if I said when you did these cuts, you had equilateral triangles? Then your shape would be something else, right? And as I move that, the triangles get smaller, and then they get bigger, and then smaller, right? Put them all together. Whoa. Why is it not showing up? Weird. Let me redo the code. Okay, triangles, grid. Why is it not? I'm not sure why it's not shading it. That's weird. Works with squares, semicircles. There's semicircles.
But that means they're not perpendicular to the x-axis anymore.
What's not?
The cuts.
Yeah, no, these are still cross sections are still perpendicular. This is a semicircle, right? See the cross sections?
Yeah.
They're still perpendicular to the x-axis. See them in there?
They don't just form squares.
You're okay?
Yeah.
Okay. I don't know why my triangles is not. Oh, now it's shading. What is going on? That's weird. It didn't shade before. Now it is. Do you see with triangles it's slightly different, right? So that's with triangles. This with squares. This with semicircles, right? There's nothing. Now the pipes. That object that I was saying we could find the volume of that one piece, and then we have 8 of them. That solid is exactly something like this. It is the base is something, and the cross sections are all something else. You have to figure that out. All right. But let's continue with the problem. All right. So how do we do this? All right. So the way we're going to do this is we're going to come here and imagine instead of cutting it and looking at a cross section, let's come in here with this special little knife that we have. And let's cut a little sliver, okay? This infinitesimally thin sliver, like a little piece of cake, right? And we've cut a little tiny sliver out, and we're going to take it and move it over here to the side and take a look at it, all right? So here's what it would look like. Do your best to just try this. Draw an X that's like been flattened out, okay? See, it's not like a true X. It's an X that's flattened out. And then out of the center, draw a line straight up. This is going to be my x-axis and my y-axis. So that's the ground. And what I'm going to do, and just do your best on this. You don't have to be perfect. I'm going to try and draw this parabola on that. So it'll look like that. And then my other parabola will go like this. I could call it Z. Was that you? Okay, I heard, but I didn't see. Yeah, we will normally call that the Z-axis. I'm just not going to because we don't need to talk about Z at all. That's kind of a not bad picture, like 3-dimensional picture, right? Not too bad. Okay, and now what does my little slice look like here? It's going to be like this. Really, really thin, right? It goes up, over, and down. It has a little bit of a thickness to it like that. Right, that's my little slice in there, like this. Not bad. Not great, not bad. All right, now, if you look at that one little slice, do you agree that if I could find a formula for the volume of that one slice, then I can use the integral to add up all the slices, right? So do we know how thick it is? What's the thickness of this slice? Well, prior to this, right, when we were doing this, we had this infinitesimally thin rectangle, right? Well, it's the same exact concept, isn't it? This is going to be how much I'm changing x by. So this is going to be dx. And since it's a square, to find the area of this face, all I need to know is this distance, and that distance will be the same as this distance, right? If I multiply all 3 of those together, I will get the volume, won't I? So what is that distance? What is this distance from here to here, or you could say from here to here? On our picture, isn't that just that distance right there? Isn't it that distance? And it changes, right? Depending on where it's sliced, this is going to change. But the top of it is always the red curve, and the bottom of it is always the blue curve, right? So what was the top function? Which one of these? This one, right? This is the one that was on top? So it should be that distance on top, 1 minus x squared, and then what? This is the one I want to see what you do here. Minus, good. Minus what? X squared minus 1. Okay, so look, what you're doing is you're saying, to find this distance here, you're taking that distance right there, which is just the top function. And since this function is on the bottom, below the x-axis, when you plug a number into this, you're going to get a negative number, aren't you? So if you subtract it, it's going to add it, so you'll get the total distance. So this is a negative number. Between here and here, that's a negative number, so you have to subtract it in order to subtract the negative to make it add, so you get the total distance from here to here. That's it, right? And that's the same thing as what's over here, right? 1 minus x. Why do I put the same thing here? Because I said it's a square, right? Yes?
So if we were not doing this on the origin, then it would possibly change from being minus the other function.
If you were not doing what?
If this was not centered on the origin, then it might not be f of x minus g of x.
Yeah, like, so let's say it was this. Let's just say that it was here like that and like this. Let's just say it was that, right? Then this right here would be our slice. And so if you want to know how big that is, right, wouldn't you still take the top function, let's say that's your f function, wouldn't you still take that top function and subtract the bottom? You would, wouldn't you? You would take, to figure out how tall that is, you would take the top function f and subtract the bottom function g. It's exactly what we did here. So it would not matter if we moved it off the origin. It would still be the top one minus the bottom. All right, let me clean this up. What is this? What is 1 minus x squared plus 1? It's just what? 2x minus 2x squared, right? Negative 2x squared? That's what that is. And that's what this one is as well. What is it? Oh, 2 minus 2x squared. 2 minus 2x squared. All right, so what's the volume of that one little piece then? If I ask you here, for this thing right here, what is its volume? Length times width times height, right? So it's 2 minus 2x squared times itself, right? So squared times dx, which is how thick it is, right? That'd be the volume of that one slice. And now what we need to do is add them up, right? Add them all up, which means we're going to use an integral. So I'm going to use an integral to add up all these slices, 2 minus 2x squared dx, but I need limits of integration. X is my variable, right? So what am I going to vary my x from? My slices are going to start where? Well, wherever they hit each other, right? And I'm going to stop wherever they hit each other again. So I'd have to figure out where these two curves hit each other. Set them equal to each other, right? So you have to figure out what these points are, and I trust you could do that. We get negative 1 and 1, all right? So that's our integral from negative 1 to 1. So that right there, if we finish this out, like if we calculated this all the way, right? This would give us the volume of the solid that has as its base these two curves. And when you take cross sections perpendicular to the x-axis, you have squares. The volume of that shape is whatever that comes out to be numerically. Okay? Okay, let's try something else. How about I change this problem from squares to semicircles? This is still the same, right? That's exactly the same picture. But this is not, right? This is not anymore. This is now going to be, let me draw that picture again. I'll erase this. This is now going to be my parabola here on top. Oh, shit, missed it. So now when I do these slices, I'm not getting squares, I'm getting semicircles. And the assumption here is that the semicircle has as its diameter the base. So it's going to look like, take a little slice here, imagine a little semicircle like that. Has a little bit of a thickness to it, right? So it's this shape right here. Doesn't have to be perfect, all right? We want to know the volume of that. What's the thickness? Dx. Okay, that's not going to change. That's good. But you need now the area of this front face, the area. If you can just figure out the area of that front face, you're in business. Well, that's half a circle, right? So the area of a circle is pi r squared. Didn't we prove that formula? We did prove that formula. So pi r squared is the area of a circle, and that's half a circle. So for us, the area of that, right, the area of this is going to be half of pi times whatever the radius is squared, right? But what's the radius of this? What's the distance from here to here? Well, that's this distance, right? But that's this. But we just did that a second ago, right? That's 2 minus 2x squared. That's the top one minus the bottom one again. So this is going to be, bless you, 2 minus 2x squared. Oh, wait, hold on. Is that right? That's not right. It's half of that, right? The radius of this circle, that what I just put in there is the diameter, isn't it?
Yes.
The diameter, that goes from here to here. I need half of that. So let me take that whole thing and divide by 2, right? So from here to here is 2 minus 2x squared. We established that in the previous problem. But now we want the radius, which would be half that distance. So it'd be half of that. And that just becomes 1/2 pi. And then when you take the 2 and divide each one, we just get 1 minus x squared, but then that quantity squared. So that's the area of that face, and then times the thickness, right? Any questions? I think we're ready for an integral. I'm about to add up from 0 to 1. That's not a 1. 0 to 1. I'm going to add up from 0 to 1. Not 0 to 1. Jeez, Robert. Negative 1 to 1. Left to the right. Right? From here to here. I'm going to add up all these semicircles that have this as a formula for the volume. It's this times the thickness. So 1/2 pi 1 minus x squared, that quantity squared times dx. That all right? Whatever that is, that's the volume. Last one. Equilateral triangles. This is the same, right? This is not the same anymore, right? I need to draw myself the equilateral triangle. So I'm going to do it right here. This is the one that gets people. Oh, you know what? Let's do this. Well, yeah, let's set it up. Here's my picture. I take my little slice. Here's my little slice. I make an equilateral triangle. Ooh, not very good. Equilateral triangle. It's kind of a crappy equilateral triangle. So if I look at that down here, equilateral has some thickness to it, right? We know that thickness is dx. I just need the area of that triangle, right? The area of this little triangle. The only thing I know, though, is this, that this distance from here to here is 2 minus 2x squared. And since it's equilateral, so is this, right? And this side as well. They're all 2 minus 2x squared. But we need the area of that front face. So what's the area of a triangle?
It's a base times height times
Okay, so if we know that if we're given a triangle, right? So hold time out here. We're trying to find the area of this, right? We know that if somebody gives us a triangle, if this is the base and this is the height, that the area is 1/2 base times height, right? But the drawback to that formula here is that it requires you have the base and the height, right? We have the base, don't we? Do we have the height of this triangle? We do not, right? We do not. The height would be the distance from the base to that top edge. That's not this, right? It's that one right there. We don't have it. Could we find it? Yes, we could, and I think you could, and I'm not going to go through that because there's a better way. There's another formula for the area of a triangle that you may or may not remember. I hope you remember it once I put it up here. Y'all ever seen this one? 1/2 A times B times sine of theta. You ever seen this? Okay, well, if you have now, don't forget this one, all right? So look, what this formula says that if you have a triangle, okay, the area is, of course, 1/2 base times height, or this formula. So the way this formula works is B is the base, okay? A is another side of the triangle, so that's this side, and theta is the angle between them. So this formula says if you know two sides of a triangle and the angle between them, if you have those three things, you can tell me the area of the triangle. Right? That's what that formula says. Now, I'm gonna show you that this is not like crazy magic, all right? The way I'm going to show that to you is just look at this picture right here. And let me just ask you real quick, from this picture, do you see that little right triangle right there? What is sine of theta, according to your pre-cal? Opposite over hypotenuse. So that would be h over a. Solve that for h. Multiply both sides by a. What do you get? A sine theta is h, right? Now, take this formula and replace h with a sine theta, and what do you get? This formula. Okay? So it's not like a crazy magic, okay? It is a very simple formula based upon the geometry of this triangle. But what's the advantage to this formula for us? Do we have two sides? Yes? Do we know the angle between them? Yes, it's equilateral. Equilateral means all angles are the same. And three angles add up to be 180, so 60 degrees, right? So we know that the area of this is 1/2. Let me do it over here. The area of that is 1/2. What's A? Well, either side, doesn't matter. 2 minus 2x squared times B, 2 minus 2x squared times sine of, sure, we'll go with 60. We'll go with degrees. If you want degrees, we'll do degrees. And what is sine of 60 degrees? Root 3 over 2. Square root of 3 over 2. It's one of our common angles, right? And we should be comfortable with all the trig functions evaluated at those common angles. This is root 3 over 2. And so if I just kind of simplify this out, this is going to become a root 3 on top over 4. So I'm just bringing that out to the front with the half. And then I have the 2 minus 2x squared, but I have 2 of them, so squared. That's the area of the front of this equilateral triangle. And then I have the thickness, right? So I'm going to use the integral. I'm going to add them all up. I'm just about done here. The volume of this solid is going to be the integral from -1 to 1, and then root 3 over 4 times 2 minus 2x squared, that quantity squared, times the thickness dx. Whatever that number is. What do you think? Yes?
We can pull out the square root of 3 over 4.
Oh yeah, you can pull out that constant, yep. Actually, isn't this similar to the problem we just did? The one with the semicircle. What do we have as a constant on the semicircle one? 1/2 pi, but this was the same, wasn't it? Right?
Well, it
No?
was over 2. 1 minus.
Oh yeah, that's right, it was over 2, that's right, it was, okay. But how about for the square?
That one was 2 minus 2x squared.
Yeah, so for the square, it's just we're off by a constant, right? Okay, this completes 7.2 and 7.3, all right? I will give you some homework problems out of 7.3, but I'm going to have to look at them. I'll probably email those to you after class. All right, 7.4 and 7.5, we're going to move very quickly through these because your homework problems only involve two problems from each section. That's it. This is more just so that you know that this stuff exists. All right. Oh yeah, you'll be tested on it. Yes. But we're not going to like spend 3 days on it. Okay, 7.4 is what we're starting right now. This section is called arc length. Arc length. So take a look at that image over there. We've done all sorts of things with functions now in this class, right? If you give me a function, I could ask you for the area, right, under that curve. I could ask you to rotate it around the x-axis, rotate it around the y-axis, rotate it around all these different lines, right? I could ask for that. I could say that that's the base of a solid or something, do cross sections. But now I'm going to have a very simple question that maybe we should have asked a long time ago. If you were to take that function and act like it was like a string on a flat sheet of paper, right, like a string, could you just like take it and just straighten it out and measure how long it would be? All right, just take it off the page like a rope, straighten it out and measure it. That's called the arc length. It would be like if you were walking along that path, it would be how far you walked, right? Seem like a reasonable question? Yeah. So that's what